In this worked example video, we're going to ask why it is that the radius of the white dwarf is proportional to mass of the white dwarf to the 1/3 1 over it. Now, you've seen the derivation, so in some sense we know the answer. But what we're going to do here is a very important step, which is to try and understand the meaning of the answer. So why is it like that? Not just the equations. Where does it actually physically come from? So how do we approach something like this? Well, we know that our white dwarf is proportional to m to the minus 1/3. Where does that come from? So let's go back a bit in our derivation. It came from these two equations. This equation came from the previous section, and it was telling us that the central pressure of a star is proportional to rho squared r white dwarf squared. And this equation up here is telling us that the pressure from quantum mechanics goes as density to the 5/3. There are lots of other constants in here like h and me and mh, but they're not going to change. What we're interested in is what drives the dependence on the mass of the white dwarf. And the mass of the white dwarf is going to depend on the radius of the white dwarf and the density. So these are the only things that matter. Okay, so our first step must be to look at how we link these two, which I left as an exercise for the reader in the video, but let's go through it a bit now. So we know from the equation for pressure of a white dwarf, the centre of any star, that pressure is proportional to r squared density rho squared. And from quantum mechanics, we know that the pressure is proportional to density to the 5/3 power. So set these equal to each other, and we get that r squared density squared is proportional to density to the 5/3. We also know that the mass, because we're assuming these things have constant density, is proportional to the volume, which is proportional to r cubed, times the density. Okay, so let's combine these. Let's rearrange that. We get that r squared is proportional to rho to the 5/3 minus 2, which is rho to the minus 1/3. And from this we know that rho is proportional to m over r cubed. So plug this in here, we end up with r squared proportional to m to the minus 1/3 and r to the 3rd times minus 1/3, which is just r. So we end up with r proportional to m to the minus 1/3. That should be a third there, which is what we said. So it makes sense given our two initial equations, but where did they come from? Let's go back to the first one here, that the pressure at the centre of a white dwarf is proportional to r squared density squared. Now, why is that the case? Now, if you remember, how we derived that was we took a star and we took some slab within it, and we balanced its gravitational pull downwards with the pressure force upwards, and that gave us the pressure gradient. So how would you expect this to depend on density? Well, you'd expect it to depend on density squared, because the downward force, clearly the heavier that slab is, just the bigger density is, the more the force is going to be downwards, but also it's being attracted by all the matter further down in the star, and so the higher the density of the star, the more the attraction is going to be. So you'd expect it to depend on rho squared, one factor of rho because it would increase the mass of the region further in, and another factor of rho because it increases the mass of the slab. So the rho squared makes sense. How about the r squared? Well, how does it should it depend on r? Take our slab again, and you've got the region further inside that's pulling on it. The volume of the region further inside, volume is proportional to r cubed, and therefore the mass is proportional to r cubed. So you'd expect, as your slab went out, the mass that's pulling it down goes as r cubed. But your distance from the centre of mass affects gravity. Remember, gravity force is proportional to 1 over r squared, the inverse square law. So you have an r cubed and a 1 over r squared. Got a big R for consistency. So that will tell you that the overall force should be just proportional to r. But then we have to integrate from the surface all the way down. So when you integrate r dr, you get r squared. So that's because the pressure at the centre, the contribution to the pressure from each little bit goes as r. But if you make r bigger, there are more bits. So you're adding up more bits, that gives you another factor of r. So that explains why the central pressure is proportional to r squared rho squared. Now we go to the other equation, which is that from quantum mechanics, that the pressure you get from degeneracy is proportional to rho to the 5/3. This seems a rather funny one. Why should it depend on this? Well, this came from thinking about electrons bouncing off something and applying pressure to it. Now, for every electron that bounces off, the amount of pressure is going to depend on the mass times the velocity, that's the momentum, but also the number of electrons that hit per second, remember, is going to be proportional to velocity, because only the ones within velocity times time of the surface are going to hit in time. So you expect that to be proportional to mv squared. Now m is going to be proportional to the density. High density material means there'll be more electrons. So you might expect the pressure just to be proportional to the density, which is indeed what you get if it was a normal gas. But remember where the velocity is coming from. It's coming from the uncertainty principle, that if we squash the atoms more, the electrons more, then they have to go faster to compensate. So delta x, delta p is greater than something. H bar over 2 in this case. So what is delta x? Well, remember we've got our big box of white dwarf, and we're breaking it up into little cells, one cell for each electron, and the volume of each cell is proportional to delta x cubed, which means that delta x must be proportional to the number density of electrons to the minus the third power. And from this equation, delta p, which is proportional to velocity, is inversely proportional to this, so it tells us that the velocity is proportional to the density to the 1/3. So we've got mv squared, m proportional to density, v proportional to density to the 1/3, so mv squared gives you proportional to density to the 5/3. So that's how you make sense of something like this. You look at where it came from and what the scaling is, ignore all the constants, and so we can see that we can explain what's going on for both the two terms that combine to give us r proportional to minus 1/3.